Let's now look at the data and then the multiple regression output in Excel for this problem. Alright, here's the data. In the first column we have the y variables, and these are measured in hundreds of thousands. So the first number is actually 177,587 Class 8 trucks sold. Second column is the average price of all trucks variable, and that's in thousands of dollars. So that first number is an average price of $50,945. And the last column was the usage variable, the number of ton miles. A ton mile is 1 ton moved 1 mile in the US. So the 2260 is probably, in the actual unit of measurement has been lost, it's probably in billions of ton miles moved. Alright, these numbers were subjected to the multiple regression output in Excel, and the following result came about. Now there are several things on this that we won't get to and don't care for right now, but we will talk about R squared. We will look at and use parts of the what is called here the ANOVA table, the analysis of variance table, and we will use this portion of the table for the regression results. This table here is quite typical of regression output because it's very easy to do once you've done the programming. One column will tell you about your x variables, and Excel calls, instead of x0, they've called it the intercept, and actually beta hat 0 is the intercept and the x variable is the constant. But anyway, then we have the second row, so this is beta hat 1, this is variable x2, so this is beta hat 2. Beside each of the betas are associated standard errors. We don't care about the standard error for beta hat zeros, but again, it's easy for the programmer to print that out. We care about the standard error for beta hat 1, so this is S of beta hat 1 here, and this is S of beta hat 2. Alright, so let's now take these numbers and write down this regression on our page. Okay, so our regression result given on the output, y hat is equal to beta hat 0, which is negative 1.935, plus beta hat 0 and plus beta hat 1. Beta hat 1 is a negative number, 0.00989 times x1, and then plus beta hat 2, which is a positive number, plus 0.00192 x2, and below the beta 1, beta 2, but not beta 0, we'll put the standard errors. Standard error of beta hat 1 was 0.03362, and standard error of beta hat 2 is 0.000300327. Right, the other bit of information we need right now is that the number of observations is 9, with 9 annual bits of information. Alright, we're now going to introduce the technical analysis, and we're going to do it in reverse order because that's the easiest at first. And later on we will put it in the proper order, R squared, the test for the regression, and the t-test. But right now we will look at the t-tests, since they're very similar to the t-tests in simple regression, and these are t-tests for the significance of each of the x's. Since in multiple regression we have typically more than one x variable, we'll have a set of hypotheses and decision rule which will work for all of them because they don't change for each individual x. Alright, so the null hypothesis will be that beta sub I is just a generic number, subscript if you like. In this case it could stand for a 1 or a 2. Beta I is equal to 0, which means that x sub I, the associated x variable, does not, and we will now include the word help when we do it in multiple regression, does not help explain the y variable. And down the way we will try to explain why help. Alternatively, the particular beta sub I is not 0, which means that x sub I, its x variable, does help explain the y. A quick way to perhaps understand the word help here is that use an analogy, which no analogies are perfect, and the analogy is that, say, the x's are like witnesses at a crime scene. Some witnesses will explain a lot of the crime scene, other witnesses not so much, but quite often their explanations will overlap. Right? So we want to know if it does or does not help explain the y variable, the crime scene. Every t-test needs degrees of freedom, and for multiple regression that's n minus k minus 1. In simple regression, k would be equal to 1. Right? Simple regression is one variable, one x variable, so in simple regression it was just simply n minus 2, minus 1, minus 1. But right now we have n minus k minus 1 generically. N was 9, x is the number of, k is the number of x variables in the regression, 2, minus 1, and so we have 6 degrees of freedom. We'll use the standard alpha of 5% in all these problems in multiple regression, so our t is one with 6 degrees of freedom, 2.5%. Alright, and that, as you can see, is 2.447. And now we'll write a quick decision rule for that, and the decision rule here will be more abbreviated than it was for simple regression. If tcalc is between our critical values of plus and minus 2.447, we'll just say that x sub I is insignificant. It means that x sub I does not significantly help explain the y. Does not significantly help explain the y if the tcalc is too close to 0. Alternatively, if tcalc is not between the critical values, in other words, it's far enough away from 0, not between plus and minus 2.447 here, then we'll say that the x sub I is significant. It does significantly help explain the y. Of course, after the decision rule, we'll need tcalc, and the formula for that generically is what you'd expect after simple regression. Is beta hat I, 1, 2, 3, etc., divided by the standard error S of beta hat I. Alright, so we have two x's, so we'll do it for each one. So for x1, is it significant or insignificant? It's beta hat 1 divided by S of beta hat 1, and from previously we had that beta hat 1 was a negative 0.00989, and we're going to divide that by the standard error, which we have from above, which is 0.003362. We use our calculators to calculate that, and that's a negative 2.942, and that is not between the plus or minus 2.447, so x1 is significant. Alright, x1 being the average price of all trucks. The average price of all trucks significantly helps explain the y variable. Now for x2, tcalc beta hat 2 divided by S beta hat 2, and again from above, that's 0.00192 divided divided by the standard error, also from above 0.000327, and the calculator tells us that that's a positive 5.872, which again is not between the plus and minus 2.447. So x2, the number of ton miles used for the existing stock of trucks, is also significant. Does significantly help explain the why. Alright, so now we have a regression and we know that the 2x variables are significant.